Thank you. We need to get radiation done and dusted in this lesson. I'm probably going to give you a weekend task of watching a YouTube lesson, just so that we can maybe scrape through and get a revision lesson before the test. The test is Wednesday assessment period, and I'll need to confirm with the ladies when they are going to be sitting it, probably Wednesday morning before school or Thursday. We will discuss that in due course. So, we have modes of heat transfer. Evaporation draws heat from a substance, causing a liquid to evaporate. We have conduction and convection, and we looked at the factors that affect the rate of heat transfer. Now, this is the last one, radiation. It's the transfer of heat from one place to another through electromagnetic waves. So there is no net transfer of matter, similar to conduction. But here's the cool thing. It travels at the speed of light, because all light is considered electromagnetic radiation. Close it, please, Cheng. And, important for us, it doesn't require a medium. It doesn't require matter. It can travel through a vacuum. So we can suck all of the air out of a bell jar and create a vacuum. We still can see light travelling through. Obviously, between the sun and the earth is a vacuum. There's not many particles, yet light is still able to travel through. Okay? So obviously we are very glad that that can occur, or else life wouldn't exist, because we wouldn't be getting any of that energy from the sun. Now, in year 9 and 11, here is my wonderful electromagnetic spectrum. Okay? And we'll have a quick look at that in just a moment. But my favourite professor, Richard Feynman, it's a good pub quiz if you ever asked. Richard Feynman described electromagnetic waves like such. He said, imagine that you comb your hair, you get up in the morning and you comb your hair, and the plastic comb accumulates a charge. Okay, you may have played with the glass and the plastic rods in year 8, and you rub them with the wool, and then you can make little bits of confetti dance, right? You've accumulated a net charge. Okay? Now you take that and you jiggle it backwards and forwards. What you have done is you've moved a charge in an electromagnetic field. This field travels everywhere. We're in the field right now, and the electromagnetic ripples are moving through this classroom just by me moving backwards and forwards this charged rod. They travel out at the speed of light. And so if I take one jiggle and I do 1 in a second, I've made a big sloshing wave. In that 1 second, it's travelled 300,000 metres. Okay? If I did 2 jiggles in a second, right, then the wavelength is now halved. Each wave is now 150 million metres. Okay? If I keep increasing the frequency at which I jiggle this charge, the wavelengths get shorter and shorter and shorter. Okay? When we get to the topic of waves, we will come back to it in more detail. But my favourite little box in this classroom, that is a joke, is this stupid thing up here, our Wi-Fi AP. It has an oscillating charge that's jiggling backwards and forwards 2.4 billion times a second. Its frequency is 2.4 gigahertz. The wavelengths, the waves are travelling out at the speed of light, and they're smacking into your head and they're sloshing around you. You don't notice them, right? Their wavelengths are about yay long, 10 centimetres. Okay? We can't detect them. But these things can, alright? There's a strip of metal that runs around the outside of your screen. It's called an aerial, and it causes the electrons in that aerial to oscillate at the same rate as the oscillator in there. So we've just transmitted energy. You can transmit data, so your laptops and your phones can communicate to that. We are at here, radio waves. So if you would like to add here, Wi-Fi, please. Wi-Fi. Now, if we keep jiggling, the wavelengths get smaller. And in the next range of about 1 centimetre to 0.1 millimetres, make sure I get that right, 1,000 micrometres is a millimetre in fact, it's now infrared. It's still, we cannot see it. But in this region, it's very, very good at transmitting heat. For some strange reason, infrared can cause objects to heat up. All right, so could we please, right here at infrared, very good at transferring heat, okay? Then we've got our visible light spectrum, which is a tiny, tiny slither, and sometimes you'll see it blown out as, oh, I went the wrong way, Roy G. Biv. All right, because it is a very tiny slither of this spectrum. If we could jiggle faster, we're now at about 10 to the 15 jiggles per second, 10 to the 15 hertz. Our wavelengths are down in the 100 nanometer scale. So 400 nanometers, we can't even measure that. We're down to the wavelengths of visible light. 700 nanometers, we would see a red colour. Down to 350 nanometers, we would see a blue colour. Those are the wavelengths that the cells at the back of our eyeballs can detect. There's a nervous, it hits the back of your eyes, and that creates an electrical signal which travels to your brain, and you perceive that as colour. Okay? But outside that, we don't see anything. All right? Now, when Isaac Newton, here he is again, he did his work on optics. He took a glass prism and he shone white light and he split the light into the 7 colours. Have I told you this before? No. Well, he did that. And he was able to prove that white light was simply a mixture of all the 7 prime colours. Red, orange, yellow, blue, green, indigo, violet. Now, I've got it back to front, but red, orange, yellow, blue, red, orange, yellow, green, blue, indigo, violet. Roy G. Biv is a good little name to remember the letters. So he was able to prove it. And then he was able to recombine it back into white light. So he was on the right track. Not only that, he did lots of experiments with light. He placed thermometers to see if there was any difference, to see if was there any difference in temperature. And as he noticed that as you got towards red, there was more temperature. And then just for fun, he placed his thermometer over here where there was no visible light, and the thermometer shot up. He goes, there must be some invisible light to us that's got energy, and we just can't see it with our eyes. And that was the infrared region, very good at transmitting heat. This is an infrared lamp. Obviously, there is some visible light coming through, but there's a ton of infrared. We want the infrared warming these guys up. Now, hot objects emit a lot of infrared. You're also emitting a lot of infrared. You're at about 30 degrees. We'll get to that in just a moment. Let's keep going. If I keep jiggling, eventually beyond violet we get ultraviolet, above violet. Now, could you please highlight UV, X-ray and gamma? Please. And what do you think I'm going to write here? Yes. I'm going to write ionizing. Okay? So, beyond visible, the energy in the waves are enough to flick off electrons. You literally turn atoms into ions. So we are made of molecules, they are made of atoms. If we get ultraviolet light striking our atoms, it turns them into ions. And if you turn enough atoms into ions, you can damage those molecules. Okay? So that's what gives us sunburn, that's what gives us a tan, which is the body sort of trying to defend itself against the bombardment, and also it gives us skin cancers, okay? Which is unfortunate. Ultraviolet. Some things will glow different colours under UV. And so bees can actually see ultraviolet. So they have, their range is shifted a little bit. They don't really see much red, but they see more ultraviolet. So when they're flying around looking for flowers, when they see a flower, it doesn't look like the colours that we see the flower. It literally, for them, it glows like a helipad. So when they're flying around, they're like, it's in darkness and they see these glowing helipads and they can just fly they fly down to the helipad, okay, because they can see ultraviolet. There is a couple of species of vipers. There's the pit viper, named so because of the pit of its eye, that can actually see some infrared. So some reptiles, snakes, their region has shifted towards the red end, and they can see some infrared. So they kind of have like predator vision. Predator, an awesome movie from the 1990s starring Arnold Schwarzenegger. Yes? Now, Predator has heat vision. He can see the heat signature. He can see an infrared. So, basically, your snake slithering around in the desert in America, if there's anything warm that approaches him, he would see that glowing like the Predator vision, and he just goes up to it and chomps on it and hopes that it's a mouse or a rabbit. There is obviously we will learn waves, high energy, low energy, high frequency, low frequency, and then the wavelengths are inverted. So these are the long sloshing wavelengths on this end, and over there are the short sloshing wavelengths. The cool thing is to appreciate that all of this information is racing through this class right now, and we're only really detecting two of them. We're detecting the heat and the light. Okay? But everything else is racing through this room at the speed of light. All the radio channels, Triple J, Nova, 96 FM, they're all in this classroom right now. All the TV channels, they're with us too. But we're not tuned into radio, we can't tune into TV. We have to get a special electric box with an aerial, and we open that, and then you tune your aerial to listen to a certain frequency, and then boom, there's Married at First Sight, Sunday through Wednesdays, 7:30, except on Sundays when it's at 7. Right. Okay. But it's all in this classroom right now, and it's all racing through, but we don't see it. Even more interesting is that they don't interfere with each other. So have a think. I can see Jackson, and the light's travelling from Jackson to my eyes at the same time that Varad could be looking at Justin, and the light's travelling through each other, and they're not colliding like bullets, because if they collided like bullets, this would just be a room full of static. We wouldn't be able to see anything. So everything's racing through and not getting jumbled up. That's why you can have a TV over here playing Channel 9 and a radio over there playing Nova 937, and I can see Jackson, and the Wi-Fi is working for my laptop, and the light's travelling to the screen and bouncing into your eyeballs. And the heat's coming off this infrared lamp, so I can feel the heat. All right? So there's two real things that we can sort of sense at the moment. Visible light with our eyeballs and infrared with our skin. Now, yes, what is it? Yes, what?
Is that why when you've got like a flame and the hottest part is like a flame?
I don't know. Ask your chemist teacher. Yes, Varad.
So
I shot that down,
the
didn't I?
microwaves and stuff.
Yes. Yes.
They just go through your brain, but it doesn't like. So
microwaves. I shot down Scott, but I will answer Varad's question. Sorry. Microwaves have a large region, it's a large spectrum. So Wi-Fi is actually in the microwave, but it's not causing our flesh to boil. Microwaves, obviously the intensity decreases as per the square of the distance, so that if you double the distance, you get a quarter of the energy. If you triple the distance, you get 1/9. If you're 10 times the distance, you get 1/100. All right? So it's not like opening up a microwave, you can't make a death rate. You have to be really close to the microwave. Now, microwaves, after the war, in America, they had developed all of this tech from the Manhattan Project. So they started playing with radio, radar, trying to figure out ways of detecting planes, and they discovered. Now, I'm not sure if this story is true or not. God, Babylon. One of the scientists, engineers in the army noticed that when they were playing with a certain frequency of microwave, that a candy bar in his pocket melted, and it burnt him. It was warm. So then, obviously, the first question is, well, is there any military applications? Can we point this microwave at Russia and just nuke the Russians? No, because the further away you get, the weaker the energy. It took until about the 1970s that somebody said, hang on, there's an application here, anything with water. That's what they discovered. It was the water molecule. You've got, give us a fist. You've got hydrogen and oxygen, and the bond lengths between the oxygen and hydrogen were at just the right, thank you, you can put your hydrogen down. They were at just the right length that when you sent this microwave through them, it caused them to resonate, like jiggling backwards and forwards, right? But instead of ionizing it, it just jiggled it up. Just water, just at that length and just at that frequency. So someone said, hang on, we could cook food with this. And they, no, it didn't take off. The army said, nah, I've got a perfectly good oven at home. I can cook my roast in 3.5 hours. Why would I want a microwave that can do it in 9 minutes? So eventually it cottoned on. They created the microwave oven. It's a box that has microwaves bouncing around in it, and anything with water gets very, very hot. The cool thing is, the little mesh at the front of the microwave, it's actually called a Faraday cage. The microwaves can't get through. So that's why you can stare into the microwave and watch your food as it's slowly rotating. But none of the microwaves come out. Because the holes, microwaves are too big, but the visible light can travel through the holes. So that's why you have that mesh on the front of your microwave. You can see your food, but you cannot feel it. All right, here are some important curves. Turn the page. This is called a black body curve. Every object above absolute zero emits electromagnetic radiation. I will say that again. Every object above absolute zero emits electromagnetic radiation. You can detect it. You can basically sense the wavelengths travelling off an object. Now here's an important thing. The hotter the object, a few things happen. Number one, the peak wavelength gets shorter. Have a look here. We've got 3000 Kelvin, then 4000, then 5000, then 6000. And you can see that the wavelengths have gone from 700, 580, 483, getting shorter and shorter and shorter. Right? So the hotter the object, the shorter the peak wavelength. The peak wavelength is the most prominent. You get a distribution curve, you get that big distribution curve, right? And then it drops back down. Not only that, the hotter the object, have a look at the intensity. The intensity gets higher and higher and higher to the fourth power proportion. It actually shoots up, it skyrockets up. And you'll notice, see, going from 1,000 to 1,000 to 1,000, you can see the jump has gone from, that to that to that to that. It gets really, really big. This applet, if you can understand this applet, then we can finish the lesson here. Well, not really. I tell a lie. If I bring this back down to the Earth, the Earth is not emitting any visible light. We cannot see it. I'm going to have to sort of zoom out. Oop, wrong way. And there's so little... Whoops, wrong way. I'm going to have to zoom in. Oh, there he is. Look at that. Okay, go away. No, wrong way. Oh, there we... Oh, hang on. Let me try... Yeah, okay, that'll do. You have a similar graph at the bottom of your page. Terrestrial. See that little red curve? Terrestrial. That is the heat signature of the Earth. Alright? It's spitting out, because the atoms in the atmosphere and the atoms at its surface, they're jiggling. Atoms have charge, protons and electrons, and they're also jiggling. So these jiggling atoms are sending out electromagnetic radiation. They're not jiggling that fast though, because they're only at about 20 degrees. So they're jiggling slow. So the wavelengths are long. Alright? So the peak wavelength for the Earth is down here in the micrometer scale. It's not visible. We can't see it. But an alien spacecraft that might enter our solar system could point its camera at this rock and it can get that heat signature. And there is an equation that relates an object's temperature with the peak wavelength. So literally, they just measure the peak wavelength, and it's called Wien's law. Wien's law will say that that object sitting there has an average temperature of 23 degrees. Okay? If you pointed your camera to the next planet, maybe let's go in Venus. Is Venus hotter? Let's go Venus. Come on, go. Whoa, 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 no, not Venus. Venus, right? Couple of things. More, it's shifted. The wavelength's gotten shorter. The molecules in Venus are jiggling faster. The ripples that they are sending out have shortened. And so they could see that the surface temperature of Venus might be 90 degrees or something. See how it goes off the scale? That's because it's T to the 4th power, right? So if I want to get up to something that's going to start emitting visible light, I've got to bring it back a bit and drop my scale down. Oh, too far. Nope. Oh, come on. All right, so. All right, now, okay, we're at 1200 degrees Celsius. This little star here, that is what we would see with our eyeballs, because now this curve, it's mostly infrared. So if you had something at 1200 degrees, like this lamp filament, you would feel its heat because it's pumping out a lot of infrared, but you would see it glowing. The reason we see it glowing, have a look at this, I'm going to zoom in, is that a tiny smidge of that distribution curve is now in visible light. Not many waves, but some bounce into your eyeballs. Right? Now watch, as I heat it up, watch what happens. I'm going to get hotter. Whoa, gone off the scale. Now, we're at 2,500 Kelvin. Have a look. Now, I'm just going to go back down. Watch, ready? Here we go. Cold. Dull red, because we got red and orange. As we get it hotter, now look what we've got. We've got red, orange, green, a little bit less blue, a little bit less violet. If you threw all of that at your eyeballs, we would see it as orange. That is why when things heat up, they go from a red hot to a orange hot to a yellow hot to a white hot. So literally the colour of an object can relate to its temperature. If we wanted something to get white hot, I have to, whoop, wrong way. We basically need to get it up to about 4,000 Kelvin. All right. Now, again, you don't see blue, you don't see purple, you see red, orange, yellow, Roy G. Biv flying it to your eyes, and your eyeballs go, whoa, information overload, and we see that as white hot. Gamble, what's up?
So that means a blue flame isn't to do with the temperature.
So the blue flame is because of the gas molecules. That's a different process. You'll learn about that in year 12 physics. This is the sun. Okay? So the sun has its pros and cons. It is responsible for all life here on Earth, which is great because it gives us infrared, liquid water, yum yum, that's good. Visible light, we can see it, that's good. We can find food with our eyeballs. But unfortunately, this region here, it's pumping out UV. Now, the atmosphere does as much as it can. It absorbs some of that ultraviolet, but some gets through. Okay? When it's cloudy and overcast, all the water in the atmosphere and the clouds, they're really good. They would shield us. But on a day like today where there's no clouds and the sun is directly overhead, you get a lot of UV coming through. And so we have a UV index, which is a measure of how much UV is coming through. When it is high, we need to slip, slop, slap. Okay? Cool. So I hope this applet explains this static image that you have on your screen. Yes? Yes, you may. Okay, let's keep going. Here we go. Same little, don't worry about the axes, but this is the graph that you have. The irradiance district, that's the black body curve of an object that's at 20 degrees Celsius, there's our Earth, and an object that's at 5,800 Kelvin, which is 5,500. That's the surface temperature of the sun, approximately. Now, just look at this, please. Here is Wien's law. So this is on your new sheet. So apologies, new sheet, you can add that to your thermo booklet. I don't know how it escaped the new booklet that I made. So guys, that in the box, it's not in the syllabus, you don't have to know it, but it's an interesting law. It basically says that the peak wavelength is inversely proportional to the temperature. And the capital B, that's Wien's constant. He was a scientist who saw the relationship between wavelength and temperature. So this is what your infrared cameras do. This is what your point and click thermometers do. They are literally searching for the peak wavelength, spitting it into that equation, and out spits a temperature. So what I did here, maybe last year, is I point and clicked and it said that the surface temperature of Sam Duncan is 32 degrees. It's a little bit cold, but anyway, 32 degrees, 305 Kelvin, plug it into your equation and it says that anything at 32 degrees is spitting out a peak wavelength of 9.5 times 10 to the negative 6. Well, that's infrared, all right? Obviously, something that's 32 degrees is not spitting out visible light. If I pointed my thermometer at the light, it might spit out 1,000 degrees, and then the peak wavelength will be closer to visible light. You don't need to worry about the regions of the spectrum. We are more just concerned with infrared, really good at transmitting heat. Over the page. Now, hey guys, factors affecting. We have to know our factors affecting rate of heat transfer. There are factors for radiation. Now, surface area is common to all of them. The greater the surface area, the more atoms that play a part, the more particles. So if you have a large surface area, you've got lots of atoms at the surface. This is a really cool thing to think about. You have a surface area of about 1.5 square meters, maybe 1.9 if you're a little bit bigger. Okay? If we cut all the skin off you and slapped you up on the wall like some crazy cow skin rug, you have a surface area of 1.5 square meters. The atoms at the surface of your skin, when they jiggle, half of the electromagnetic radiation goes into your body and you basically reabsorb. But half goes out, never to return. Okay, unless it's reflected in by a... ignore that statement. One of those tanning things. An emergency blanket would be one idea. If you are an atom inside your body, then you are basically emitting radiation and your neighbouring atom is absorbing it. And the neighbouring atom is emitting, and you are... So it's just all of these microtransactions of emission, absorption, emission, absorption. But if it's inside you, there's no net transfer of heat. But if it's on the surface, then zoop, half of it goes away, and there would be a net transfer of heat. Next is temperature. Obviously, again, the hotter the temperature, the greater the rate of heat transfer. And that's basically, again, back to how fast your atoms are jiggling. But it's T to the 4th power. So it's not just proportional to T, it's proportional to T times T times T times T. Because this is a bit weird, but there are different modes of jiggle. So a particle can jiggle in many ways. It can jiggle up, down, left, right, backwards, forwards. It can rotate, it can vibrate in and out, it can rotate one way or the other. It can be in circular. So because of all these different ways that a particle can jiggle, there are so many ways that it can make these ripples. Okay, that's why it's T to the 4th power. Now, here is the important part of today's lesson. Surface colour and texture. They play a very important role, and we are going to look at how we can, we use this to increase or decrease the rate of heat transfer. Now, surface colour and texture. That is what I've changed in this little demonstration up here. We have a shiny white surface and a gloss black. Okay? Now, this is a very unrealistic example of what's happening at the shiny silver. Alright, so here come in my light rays, nice parallel lines, and if it is perfectly shiny and absorbs no energy, then all of those rays bounce off. Okay? So this would be a perfect reflector. No energy absorbed whatsoever. We assign that a value, we give it a 0 value. It's called emissivity. I've highlighted the word emissivity. It's got this symbol E. If you have an emissivity of 0, it basically means that you will absorb and emit no thermal energy. It is not possible. You can get close to 0, you can get the shiniest polished silver mirror. Some of the atoms of silver in that mirror are going to absorb and jiggle. Okay? Yes?
So is there no substance that actually is a zero?
Not possible. We can get close. The whiter and the shinier, the lower the emissivity value. Okay? Next, to the other side. Let's go to the other. If I had a rough matte black, so I don't want a shiny black, I want like a rough matte black. Alright, like a rough matte black. If we zoomed in at the surface, I've drawn a very unrealistic example here. Here is my rough matte black, M-A-T-T-E. The diagram shows all my light coming in and none escape. Alright, again, not theoretically possible. We can get close to 1, but not even 2. Because again, it's the limit, it's not physically possible. So our number ranges between 0, meaning emitting and absorbing no thermal energy, up to 1, where it emits and absorbs all thermal energy. Okay? Now, I want you to use your imaginations. Imagine this animated. Imagine these rays coming in and bouncing off and travelling out. Okay? Happy there? We could play it in reverse. I could reverse that. They would come in the other direction. They would bounce off and reflect off. Okay? Happy? Yes? Alright. Now let's consider this black body down here. A perfect black body is one that absorbs and emits all thermal radiation. So let's play it in real time. In comes our rays. Ready? Here they go. And they go ding, 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 and they're all absorbed. Gone. Stop the video. Yeah? As a result, that object is going to get hotter because it's absorbed all of the energy. Now the particles are jiggling with a great amount of energy. Yeah? We've increased their kinetic energy. Temperature has risen. Yes? Happy? Alright. Now, this is the thing that students struggle with. In physics, most things can be played in reverse, and the laws of physics work in reverse. So I want you now to play this in reverse. Let's take our hot black object and hit rewind. Ding, 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 ding. It all comes out. Okay? What happens to the temperature of my object as all that energy is removed? It drops. Okay? So, it's easy to understand the two test tubes here are absorbing energy because it makes sense that you're gaining energy and the particles are jiggling faster. I need you to appreciate that the opposite also works. That hot, matte, black objects will release energy at a greater rate. So emission and absorption. Alright? So you'll see a emitter and absorber. It's which way you're playing the tape. Are we gaining heat? Then we're absorbing. Are we releasing heat? Then we are emitting. Alright? This equation here, have I got the equation? Nope. This equation here combines all of those factors. Okay? So it doesn't matter whether your Q is, if it's positive, that means it's heating up. If it's negative, it means it's cooling down. But this is combining that equation. Now, I put a question with this equation in the test. It's not in the data sheet, so I provided that equation. And I gave it to the other physics teachers for discussion. And they went, nah, take that one out, because you've already given them an equation that's not in the data sheet, that's at the top of the question, which they need to use and apply. So it's a bit cruel to give you two equations that you need to use and apply. So we removed the equation. But, could I just get you to do one thing on that page? Just underneath, I don't like that Q and time are on the opposite sides of my equal sign. I'm going to divide through by T. So could you just write down here, that Q on T equals E A sigma bracket T object to the fourth power minus T surrounds to the fourth power. Okay, so all I've done is change that to a rate of heat transfer, which you guys all need to be able to explain. The rate of heat transfer depends on the emissivity. The higher the emissivity, the faster it releases heat or absorbs. The surface area, the greater the surface area, the greater it emits heat if it's hot or absorbs if it's cold. Sigma is a constant. We had two nerdy physicists back in the early 1900s that were able to figure out the constant that if you plug in meters squared and Kelvin, out spits a unit of joules per second. It just basically converts those units into joules per second. How are we going for time? We have about 6 more minutes on my Logger Pro. Now, let's just look at this equation again. This works. Remember we said if delta T was positive, then Q is positive. A positive Q means gaining energy. If delta T was negative, then Q is negative, and a negative Q means losing. Have a look at the T's. If your object is hotter than its surroundings, then that bracket gives a positive Q. Yeah? Yeah? Yeah. If this object is colder than its surroundings, you get a negative Q on T. So a cold object in a warm environment is going to absorb at a rate of Q on T. If it's hot in a cold environment, it releases. Now that's what you guys are right now. You are at 35 degrees surface temperature in air that is 20. So we could, if we wanted to, figure out the rate at which you're losing energy. Your emissivity ranges between the palest, whitest Scottish person of 0.6 to the darkest Central African skin tone of about 0.8. Alright, so you take, if you're in somewhere in between, you're about 0.65 or 0.7. That's the emissivity of skin. It's quite a high value because our surface is not nice and smooth and shiny. Our surface has all of these ridges. And with ridges, you're effectively increasing the surface area. There are more atoms at the surface because you've got fingerprints and skin cells and things. Hang on. What was I getting at? If we knew your surface temperature and the surroundings, we know these numbers. We estimate that, and we said that you're about 1.5 square meters of flesh. You plug all the values in, and it's about 120 joules per second. So I may have said this before, that you are all little heaters, 100-watt heaters. You heat the room up by your mere presence. Okay? So when there's 26 of us in this classroom, that's the effective radiant heating of a 2.6 kilowatt heater. That's why this room, and that's why I'm starting to sweat, this room is getting quite warm because you're all heating it up. All the radiation is leaving your body and traveling into a cold environment. The last, I say that a lot, the last thing I want to look at for this equation, what if the temperatures are the same? If your object and your surrounding are at the same temperature, yes, what does this value equal? What numerical value? 0. So the rate of heat transfer is 0. So if you are at the same temperature as your surroundings, you are in thermal equilibrium where there is no net transfer. Even though you're beaming out infrared, you're absorbing it at exactly the same rate. Okay. So again, if we turn the heater up to 35 degrees and we sat there, you'd probably be uncomfortable. Your body's still pumping out energy. It needs to get rid of it one way or another. You're going to start sweating. So, guys, and ladies, homework. I need you to do 2-3, 2-4, 2-2, 2-3, and 2-4. Those are the questions on conduction, convection, and radiation. This test that's coming up next week has a huge amount of explanation questions. Lots. It's closer to, nearly 50-50, maybe 60-40. 60% calculations and equations, 40% explanations. You will notice that these chapter questions are about the same. There's lots of explain, why, describe, what are the factors that affect, list the steps, how do we affect thermal convection, blah, blah, blah. Please answer them. Please do them. I want to check them eventually, maybe Friday, maybe Monday, haven't yet decided. We have 1 minute left. If you haven't already, I know you're typing, I would encourage you to download this program called Logger Pro. Do your Macs have a disk drive? I might be able to get you the install on a USB because this is a useful program. Alright? This is the software that can control these lab quests. Okay? So, when you have investigations, you can basically plug the lab quest into Logger Pro. The lab quest just simply acts as a transfer, and you can control your thermometers. The sample rate, the duration, you can do triggering, so start recording when temperature drops below 80 or goes above 20. You can decide to extend the collection. If you're getting towards the end of the 10 minutes and you want to go for another 5, you can do all of that. The only reason I haven't plugged it in already is because with that running and Airtame and OBS, my laptop just gives up. But the recording has finished. I'm going to turn this off. Probably half the reason I'm sweating. I can now transfer this information from the LabQuest to, where's my mini USB? Where are you? There you are. So, and you can also do this if you want to collect the data from the LabQuest. You can export it as a text file. You can export it as a CSV file. That's Excel. So, have a look here. Oh dear, that's not good. Let's go, okay. Please don't. Oh, okay. Remote data. Yes, I would like to retrieve my remote data. Yes, I would like to add. Yes. Here we go. Boom. I don't know what that top graph is, so let's get rid of it. All right. Here we go. Here is our data. Now, since we have learnt that matte, rough, dark objects absorb heat at a greater rate, which one do you think was the rough, dark object? Temperature 2, which is currently 8 degrees hotter. And they started at 24, and then they got up to 42. And in fact, they're starting to cool now. And if I take them out, they'll probably drop even more. Okay. Now, I want to try something. Isaac Newton said that the rate of heat transfer depends on the difference in temperatures. And as something heats up, the difference in temperature drops, so the rate drops. And so you get this beautiful exponential curve. You can highlight bits of data. You can go up here and go analyze curve fit. And you can try and fit, I want temperature number 2. You can try and fit a curve. Is it linear? Is it quadratic? Is it cubic, quartic, quintic? Is it AE to the negative CX plus B? I believe it is. Boom. Okay. Look at that. It's fit a curve so well that you can barely see it. That is a mathematical curve known as Newton's law of cooling. It is AE to the negative KT plus B. And it's just told us that this little C term here, that capital C, that is called the decay constant. The greater that number, the greater it absorbs. The smaller that number, the less it absorbs. These are very useful software that if you want to, you can use it in your investigations. Yes?
Where does it get the uncertainty from that? From the logger itself.
God knows. It does linear regression, least squares, it does maths and statistics, and it gives you the uncertainty based on the numbers that you put in. But basically, one of the... Oh, look at that, correlation. You guys have probably learnt that word, correlation, in maths. 0.999999. It's saying between that bound and that bound, it's almost a perfect fit. If I tried to change that to linear, if I went linear, temperature 2, it's going 0.974. It's like, well, yeah, it's pretty good. Yeah, but it looks like... No, it's, least squares regression, least squares regression. It is definitely not linear. It is exponential. And not only that, before you go, how much time do I have? Negative 0 or negative 5?
Negative 5 seconds. 10 seconds.
Shush. Hold on. The cool thing about this equation, a e to the power of, if you set time, if you set time to infinity, what's e to the power of negative infinity? 0. Right. So if we set that to infinity, then our temperature would be 0 plus b. B is 45. That says that this curve is on its way to 45. And it's just going to asymptote at 45. If we could keep this heat map going forever, the temperature asymptotes at 45. Yeah? If you set t equal to 0, what's e to the power of 0? 1. So if you set the time to 0, then you get a plus b. What's 23 plus... what's minus 23 plus 45? 23 degrees. Hey, that's the initial temperature. 23 degrees. Okay? It's all fun stuff. Sorry I spoke at you for 50 minutes. I hope you deal with it in your own way. Okay.